This is the video report for Lab 2. So we'll start with the introduction. This is largely the same thing as the first lab, so I'm not going to go into a ton of detail on this. The first 3 points are basically the same. We're still using electric and gravitational forces by doing an experiment with charged tapes and measuring how they interact with one another. But unlike Lab 1 in our calculations, instead of treating the tape's charge as a single point charge, we're going to treat it as distributed evenly along the surface, and our model is going to be a line of point charges. So for the assumptions, these are pretty similar as well. We're still assuming that the magnitudes of the gravitational force and electric force on the top tape are treated as exactly equal. And since the 2 tapes were made in the same way under the same conditions, they're still assumed to have equal charge, evenly distributed along the strip of the tape. And the calculations are still made as treating the 2 tapes as exactly identical. We're still ignoring the external conditions like the humidity, the wind blowing, and things like that. And this time we're having to ignore the likelihood of the adjacent point charges interacting with one another and fluctuating in charge a little bit. We're treating them all as equal. So for the experiment, we start by creating 2 charged tapes exactly like last time, hanging one above the other. Then we measure the distance in between them when the top tape starts to float. We record that length, use that length to find the mass, and then we're computing our desired calculations through GlowScript. Last time it was largely by hand, but this time it's entirely in the code. So here's a picture of the floating tape diagram just to kind of visually see how that looks. And then in the free body diagram, I've just taken that same picture, but I've added the vector arrows for the electric force and the gravitational force on the top tape. Notice that they are pretty much exactly the same length, they're just pointing in opposite directions. So for the data and observations, we know from Lab 1 that each tape has a negative charge, and that the top tape started floating when the 2 tapes were 0.7 centimeters apart, and one piece of tape was 24.2 centimeters long, which means it weighs about 0.242 grams. So now for the coding section. The objectives are to write a program to produce a computational model of 2 charged tapes exerting an electric force on each other and experiencing a gravitational force modeled as a line of point charges. And then we use this model to estimate the amount of charge necessary to float one tape above the other. So the main goal is to plug in all of our information, write a correct program, and figure out what is the minimum charge needed to float tapes above each other. So I took the model of approximating the charge instead of working it out analytically. So I set up the top tape and the bottom tape as line charges in the code, separated by the floating distance that I found to be 0.007 meters, and I represented them with 75 consecutive point charges each. I didn't want there to be too many and have just a whole lot of stuff going on, but a large number is enough to get a more accurate model. I initially plugged in the charge I calculated in Lab 1 using the point charge model. We know that since there are more assumptions made in Lab 1, this is not exactly correct, but it gets a good starting point. And my value from the first lab was 1.023 times 10 to the negative 8 coulombs. And then I compared the magnitudes of the gravitational and electric forces calculated as line charges in the code and found that the force of gravity divided by the electric force is approximately 1.85018. And then I multiplied the square root of this ratio by the estimated charge from Lab 1 to find the actual charge, which is 1.3915 times 10 to the negative 8 coulombs. So this is a picture of the estimation output in my code. You can see at the bottom that it prints out the original magnitude of the electric force that is not equal to the magnitude of gravitational force, which we know is not correct. And it has the ratio of gravitational force and then multiplied the square root of that by the original charge and prints out what the actual charge should be. So you can look at the arrows, and the line of pink spheres is the top tape and the line of purple spheres is the bottom tape. And those blue arrows are the electric force felt by each individual charge by the bottom tape, and the white arrow is a net electric force felt on the top piece of tape. And you can see that that arrow is much smaller than the gray arrow, which is the gravitational force. And then the final program output, this is after I changed the charge to the correct value, and you can see the magnitudes are now equal, and it prints out the correct charge of the top tape in the line charge model. And here's just a link you can click if you'd like to go into that. So for the conclusion, just kind of answering some questions about where can we go from here and what do these results actually mean. So what if each tape had been modeled as a single point charge, as in Lab 1? So the code and calculations would have been much more straightforward. When you only have one point charge, we don't really need to sum the electric force at different locations because you're just looking at one place. So we wouldn't need to have the nested for loops and the other more complicated things like we had in our code. And we also wouldn't need to clutter up our display by displaying multiple arrows. And then to compare the estimated charge values between the point charge model and the line charge model, so they are in the same order of magnitude. They're both times 10 to the negative 8 coulombs, but they are different values. And the percent error of those two values, if you're treating the line charge model like the expected or theoretical value in the percent error formula, you get about 26.48% error. So those aren't super close values. So why do these estimates differ? These estimates are different because one model is more approximated than the other. One model is just more closely representative of a strip of tape than the other. So which value is more likely to be closer to the real value? That would be the line charge model because it requires more information in the calculations, it uses a more precise formula, and it makes fewer assumptions. And also because a piece of tape is not one single atom, it is a line of consecutive atoms. So the line charge model just makes more intuitive sense that it would be the correct one.